Earth is covered with evidence of past collisions with asteroids. And today's scientists are working feverishly to figure out what's coming next. They know that enormous space rocks have wiped out most life on the planet in the past.
The good news is that they don't hit very often. It's measured in many millions or tens of millions of years. And they're big enough that through our observations, we know where those objects are, so it have long lead time and warning. It's actually the smaller ones that are the bigger risk because they happen more often and they're harder to find.
Imagine that one of these smaller asteroids is streaking toward a city. It may not be spotted until just a few hours before impact, leaving little time for evacuation and no chance to try and deflect it in space. If it's about 100 feet wide on impact, then it will hit with the energy of a 5-megaton nuclear blast. 400 times more powerful than the atomic bomb dropped on Hiroshima.
When it hits the Earth, it can cause a lot of damage because the crater that's produced is typically 10 or 20 times the width of the incoming object. So that would be 1,000 or a few thousand feet. And many miles surrounding the impact region are affected by all the debris that gets ejected. You'd have all this stuff raining down upon you.
But even if the asteroid hit hundreds of miles from the city, it could still create chaos for the millions of people living there. The food supply for the city residents could be drastically altered if the asteroid hit a major agricultural area nearby.
Not only would all of the humans there be very likely dead, but it would sear hundreds of square miles of the growing lands. It would destroy all the current crops and it would render the area pretty unusable for quite a period of time.
And smaller asteroids don't even need to impact the ground to cause widespread destruction. In 1908, an airburst from an asteroid that broke apart in the atmosphere leveled an estimated 80 million trees over hundreds of square miles near the Tunguska River in Siberia.
When an asteroid or a comet is coming toward the Earth, it first encounters the atmosphere, and it squeezes it, it compresses it, and that pressure causes the asteroid or comet to explode. That explosion then spreads the energy over a vast region of the ground below it. So these atmospheric airbursts are very dangerous as well.
But the rock that caused all of that destruction may have been even smaller than first thought. When it hit the atmosphere, the Tunguska object may have been only a few dozens of yards across, instead of hundreds of yards, as originally estimated.
At first, it may seem like a good thing, Tunguska smaller than we thought, but it's actually a bad thing for our future predictions because there are more smaller objects than larger ones. So if a small object can cause that much damage, then that means it's going to happen more often than if it were a big object. We may have that impactor every few hundred years instead of every few thousand years.
At the really small end of the scale, below about 100 feet, space rocks are often known as meteoroids instead of asteroids. Shooting stars are caused by meteoroids burning up in the atmosphere. They're sometimes captured by amateur cameras, with some small chunks hitting the ground or even cars or buildings. In fact, the Earth's atmosphere is pelted with objects from outer space far more often than most people realize.
I'm here at this active rock quarry next to this big pile of crushed rock because this is about the amount of stuff, the amount of dust and sand and pebbles that hit the Earth's atmosphere every day, about 100 tons. That's enough to fill about 6 or 7 of these dump trucks. Now down here, we've got a basketball-sized rock. On average, about 2 of these slam into the Earth's atmosphere every single day. Next is the small car-sized object. Imagine this pile of rocks as one object slamming into the Earth's atmosphere, about the size of a small car. This happens about once every 2 weeks, but even something this big is probably going to burn up completely before reaching the Earth's surface. For a typical object hitting the Earth's atmosphere, it needs to be at least 100 feet in diameter to actually do serious damage to the surface. Now 100 feet is a really big rock. That's like going from the front of the dump truck over there all the way to that orange cone over there.
At the other end of the spectrum is Earth's largest confirmed impact crater. Located in Vredefort, South Africa, it stretches more than 180 miles across and drastically changed the ancient Earth when it hit about 2 billion years ago.
It would have sent a sheet of material into space, which would then have come back and impacted on the Earth, ignited fires if there was anything to burn. And the climactic effects from that impact would have lasted for decades. The oceans would have been completely acidified. There would have been tons and tons of soot up in the atmosphere. And so that is something that we really would not want to see happen.
For the primitive life on Earth at the time, it was a major extinction event, with a crater more than 1.5 times larger than the one that wiped out the dinosaurs. The South African crater wasn't discovered until the 1990s, since most of its features had eroded in the last 2 billion years. But photos from space revealed its existence. A hilly region in the center of the deep crater initially had scientists thinking that there'd been volcanic activity in the area. But it's actually what's known as a central rebound peak, a distinctive feature for craters about 100 miles wide or larger.
As you get to larger sizes, the energy of the impactor is so high that when it comes in, the rock essentially acts like it has no strength. Then what you get is something very much like when you drop a pebble in water and you see that rebound peak as the water fills in, comes back up. But since it is rock, it then solidifies. And we see lots of these central peaks on the moon and elsewhere in the solar system.
But there are other large asteroids that have hit much more recently. Even more recently than the dinosaur-killing asteroid from 65 million years ago. 30 million years later, another massive asteroid pummeled the east coast of America and helped form what is now Chesapeake Bay.
We see evidence of debris from that impact all the way up and down the eastern seaboard, all the way up to New Jersey, New York, and comparable on the south end of it.
The 55-mile-wide crater was hidden from view underwater until oil exploration confirmed its existence in the 1990s. And since the asteroid hit just offshore, it created a massive tsunami.
Some say that the waves could have been 10, 20, maybe even 30 miles high. That's a big wave. The Appalachian Mountains are only a few thousand feet high, so even though a lot of the wave was diminished as it went inland, that's a lot of water, and it could well have flooded over the Appalachians and into what we now think of as the Ohio River Valley.
And if that same impact happened today, the East Coast would never be the same again. An asteroid attack has the power to instantly kill millions of people. The largest impacts can also cause global catastrophes, threatening the very existence of mankind. That's why the study of asteroids is one of science's highest priorities. 35 million years ago, an enormous asteroid slammed into America's east coast. The 55-mile-wide crater was hidden until recently, under Chesapeake Bay. Its effects were devastating. But what if that same impact happened today?
It would wipe out the East Coast essentially through a combination of tsunamis, blast waves, thermal effects, and it would also throw out huge amounts of ejecta that would spread to great distances, igniting additional forest fires.
It would be millions of people instantaneously killed or shortly after the impact. But it would have farther-reaching consequences, too, because of the overriding disruption throughout the entire region. Farming, communication, certainly our center of our government is on the East Coast.
But according to recently uncovered fossil records, the 1-mile-wide Chesapeake Bay asteroid didn't seem to have the same global effects as the massive extinctions triggered by the 6-mile asteroid that killed the dinosaurs.
The impact that created the Chesapeake Bay structure more than 30 million years ago was enormous, but it was still only a small fraction of the energy that was released during the impact in the Yucatan 65 million years ago. The impact was right on the threshold of providing truly global effects. Right on the threshold of what's required to make a mass extinction occur.
Because of that destructive power, it's crucial to know exactly what we're dealing with. And that means getting up close and personal. In 2001, the NASA mission named NEAR was supposed to just orbit the asteroid Eros.
But once it had got there and it had completed its mission objectives, the decision was made, let's try to land this thing, which is really, really fun. It's kind of old-fashioned exploration. Hey, go ahead and give it a try. So they did.
The images from the approach and landing gave scientists a much more detailed look at the surface of an asteroid than they'd ever had before, with some unexpected results.
One of the surprises looking at these small bodies is that they have geology. It had tectonic features and looks like it had landslides and erosion happening on its surface and impact craters all over it and boulders everywhere. And one imagines the scenario where a little asteroid comes along and hits a bigger asteroid, crashes into it, digs up a whole bunch of debris, and that slowly settles down, and these boulders just spread across the entire surface.
The NEAR spacecraft even transmitted information back to Earth for about 2 weeks while on the surface.
But it has lost its radio link with the Earth, and so now it's simply sitting there mute for millions of years.
The asteroid explorer Hayabusa of the Japan Aerospace Exploration Agency recently one-upped NEAR. It's the first spacecraft to ever land on an asteroid and then return to Earth. It arrived in June 2010 after a 4 billion-mile round trip.
As planned, most of the spacecraft burned up in the Earth's atmosphere, but the sample return capsule successfully landed in the outback of Australia.
Even today, it's still unclear if minute samples are present. The careful examination of the capsule is continuing.
It's a long process, but people are optimistic that we're going to get great data out of the first asteroid samples returned to Earth.
To a geochemist, a couple of micrograms of material is plenty to do some detailed chemistry and mineralogy and compositional work.
Even before Hayabusa returned, another asteroid mission was already underway.
3, 2, engine ignition, and liftoff.
After a 2007 launch, the NASA Dawn spacecraft is on its way to 2 of the largest asteroids in the asteroid belt between Mars and Jupiter. Dawn will arrive at 320-mile-wide Vesta in 2011, orbit for a year, then reach 600-mile-wide Ceres in 2015.
You couldn't find two asteroids more different from one another. Ceres is thought to be relatively wet, perhaps subsurface ices. And the other one, Vesta, is thought to be the opposite. It's completely lacking in hydrated minerals or water ice. It's been heated over its lifetime to such an extent that it's thought to be layered. A surface layer, a mantle, and a core, much like the Earth.
All of these missions are revealing that asteroids are made from a much wider assortment of materials than we first realized.
There's a huge variety in asteroids. Some of them are iron-rich or nickel-rich, very much like this iron dumbbell. Others are very similar to this earthbound rock. They're stony, they're rocky. Still others are a combination between the iron type and the stony type. We've also got exotic things like rubble piles, which are like having this handful of gravel, but if it all were gravitationally bound in a big asteroid kind of a form. We also have X-comets. And X-comets have gotten rid of all their ices, and we're left with this fine-grained material held in a very porous type fluff ball.
But asteroids are surprising us in other ways besides their composition.
The Galileo mission on its way to Jupiter went past an asteroid called Ida and discovered that it had a little tiny moon called Dactyl. This was a big surprise, and now we see that that's not so rare an incident. Asteroids do come with their own moons, sometimes several moons.
We're also learning that a lot of asteroids are traveling in pairs, as binaries, or even with 3 of them. And that's a very new set of observations and a new thing to understand.
Knowing how asteroids are grouped and what they're made of is more than a matter of scientific interest. Imagine in the future that an enormous, deadly asteroid is speeding towards Earth. It needs to be deflected if mankind is going to survive. But if we don't know exactly what the asteroid is made of, then the effort to save the planet could go horribly wrong. An asteroid impact can unleash more destruction than just about any other kind of natural disaster. But it's also one of the few types of nature's fury that we may be able to prevent. Imagine in the future that a huge asteroid is racing towards Earth at 70,000 miles per hour. International space agencies have banded together and launched a rocket in an effort to save mankind.
The trick is to understand the enemy. Is it made of solid iron? Is it made of shattered rock? Is it made of a rubble pile, an excometary fluff ball? Because if you hit a slab of solid iron with a spacecraft, it's going to react far differently than an object that is a fluff ball.
The asteroid turns out to be a rubble pile. It's soft enough to mostly absorb the impact of the rocket and to stay on course to collide with Earth. It's also large enough that it doesn't burn up in the atmosphere. It hits and forever changes life on our planet. This is the price we could pay if we don't learn as much as possible about the variety of asteroids in our solar system. But at least with large asteroids, we should have years or decades of warning about their approach. With comets, even enormous ones, the warning time will be measured in months. Why? That's what Clayton L. in Atlanta, Georgia, wanted to ask the Univers. So he emailed us. Why would there be so much less warning time before an Earth impact for a comet compared to an asteroid?
Good question, Clayton. we'd love to know when something might hit us. It turns out that asteroids are so nearby that we can track their orbits precisely. That means we can make accurate predictions of where they will be, tens or even hundreds of years in advance. That means we might be able to deflect them before they hit the Earth. Now, a comet comes in from the outer depths of the solar system and doesn't become bright enough to see until it's maybe 6 months or a year away from hitting us. So we have very little warning. Fortunately, most of the things that potentially could hit the Earth are asteroids, not comets. And we can track the asteroids pretty accurately.
The fact that asteroids have a much greater chance of destroying life on Earth sometime in the future is one of the main reasons why studying them with unmanned missions is so important. But in April 2010, US President Barack Obama announced an even bigger challenge.
By 2025, we expect new spacecraft designed for long journeys to allow us to begin the first ever crewed missions beyond the moon into deep space. So we'll start by sending astronauts to an asteroid for the first time in history.
In my experience as a college teacher, the younger generations, they want to go beyond. Yeah, my grandparents went to the moon, let's go beyond. And so that was an inspiring part of the president's message, that we need to get NASA back into the business of deep space.
A manned mission to an asteroid will be very different from moon missions of the past. In some ways, it will be easier, and in other ways, much harder. Whichever asteroid the astronauts visit will likely be a lot farther from Earth than the moon. So the journey will probably last for months instead of the 8 days it takes to get to the moon. But the round trip will actually use less fuel than a lunar landing mission.
When you go to the moon, you're dealing with a body with significant gravity of its own. You're having to use more fuel to safely slow yourself down and descend all the way to the surface. When you head to an asteroid with very low gravity, even though you're going farther to get there, you aren't having to expend nearly as much fuel for things like getting to the surface. It also takes less propulsion ability when you leave the asteroid to head back to Earth.
But landing on an asteroid surface will be much more challenging than setting down on the moon.
It's more like docking than it is landing. But you do have some gravity, so you have to deal with having a little bit of gravity. But you have to deal with actually anchoring yourself, holding on. You don't have to hold on when you're in the 1/6 Earth gravity of the moon.
Exploring a small rotating asteroid will also be much harder for astronauts than hopping around on the moon. It'll be more similar to a spacewalk.
Your sense of up and down is sort of screwed up. And you have to be very careful when you walk around on an asteroid because the gravity of the asteroid is so weak. A good jump can send you into an orbit around the asteroid or even send you out at escape velocity and escape from the asteroid completely. So you have to make sure that you're tethered down when you're exploring.
But since rovers have already proved to be so successful at exploring other worlds, is there a strong reason to send astronauts to an asteroid?
Astronauts, explorers, the public interested in space yearn to see what it's like in person through real human eyes. And that day is coming.
Robots can do a lot and have done a lot in space exploration, but there is no better geologist than a human being. To be a geologist exploring an asteroid and being able to recognize the history of a particular region, looking at familiar types of geological formations, you know just what you want to do. You want to go sample that rock, you don't want to go sample that rock.
Asteroids are also important because of the resources they might contain. The year is 2050, and a crew of astronauts has just landed their spacecraft on an asteroid. They're not here to explore. This is merely a pit stop. But what types of precious resources could this small rocky world possibly contain? An asteroid attack can wipe out entire species, including humans. But instead of accepting that fate, scientists are trying to learn enough about them to prevent disaster. And asteroids that aren't headed towards Earth may even turn out to be helpful.
One of the reasons to visit asteroids and to study them is that they may have some resources that could be useful to future human explorers. And among the most important of those would be ice, water. People are going to need ice to live and drink and use in a practical sense.
The year is 2050, and a crew on its way to Mars has just stopped at an asteroid for water and other supplies. The oxygen in the water can be separated to refill the crew's breathing tanks. But there's even more that this rocky supply station has to offer.
It's conceivable that with advanced technology, we could go to those asteroids, break down the water, and use the hydrogen and oxygen as fuel to take spacecraft even farther.
And there may even be priceless materials to bring back to Earth. Elements so rare and critical to high-tech success that they could be the cause of future wars.
Some asteroids have platinum and titanium and rare earth elements that are important in many aspects of electronics, which are called rare earth elements for a reason, because they're rare on the Earth. They might not be so rare in certain kinds of asteroids.
But the most important reason to investigate asteroids remains their ability to instantly kill millions of people, or wipe out the human race altogether. To counter this threat, NASA launched the WISE mission in December 2009. The Wide Field Infrared Survey Explorer has already found 25,000 asteroids and more than a dozen comets that were too dark to find using visible light.
It's actually looking all around our solar system, hopefully to look at 99% of the sky and try and map more of these near-Earth objects, these asteroids that we haven't found in the past. And hopefully that'll help us in understanding if there are any that are in near-term collision courses with the Earth.
And even though it doesn't usually make front-page news, there are already plenty of asteroids that pass close to Earth. In April 2010, a 70-foot wide asteroid passed within 220,000 miles of Earth, which is closer than the distance from the Earth to the Moon. And a few months before that, a 23-foot wide asteroid came much closer.
In the winter of 2009, in November, there was an asteroid that passed so close to the Earth. It was only 8,000 to 9,000 miles away at its closest approach. And we didn't know about that until it got fairly close.
That's about the same distance as flying from Los Angeles to Mumbai, India. And back in 1972, a tourist's camera near the Grand Tetons in Wyoming captured a much closer pass by a similar-sized object.
The 1972 event was about as close as you can get to a collision without actually colliding. On its way in, it was going to collide with the Earth, but it skipped off of the atmosphere due to the pressure of the air, like a pebble being skipped off of the surface of a lake. That was a really close call.
Then, in October 2008, a small and seemingly uneventful impact occurred in a remote part of the African country of Sudan. But it actually represented a giant step forward in the science of predicting asteroid impacts.
A small asteroid was discovered, and it was predicted to land in Sudan the next day, and it did. Now, this is the first case we have of an object that was discovered and then predicted to land at a particular time and place. And in fact, fragments of this object were later found over the desert.
But that was only a small impact with a single day's notice. Today, the jury is still out on whether we'll be able to identify and deflect something that could inflict catastrophic damage on Earth. Scientists believe there are still millions of unidentified asteroids out there capable of destroying a city. Or worse. There's a wide range of imaginable worlds. We might find ocean worlds completely covered in water, frigid ice planets, Mars-like worlds, but perhaps with thick atmospheres fed by massive active volcanoes, and even planets with two suns in their skies. There may be planets that humans would find hospitable, and others on which humans wouldn't dare tread, that could still be home to other types of creatures.
Perhaps the major lesson we've learned so far from looking for planets around other stars is that nature can make a lot more planets than we can dream of.
Finding just one other truly Earth-like planet would hint that Earths are common in the universe. And if Earths are common, then perhaps life too is widespread. But of the over 200 alien planets detected so far, most of them seem utterly hostile to life as we know it.
So far, we've found sort of three kinds of worlds. One kind are the planets that are really close to the star that they orbit, and they're totally baked to death. Then there are the ones that are quite far away, and they're pretty cold. And then there are the ones in the highly eccentric orbits, which sometimes get close to the star and sometimes far away. So they're alternately very hot and cold. So far, we definitely haven't found any worlds with jungles and forests. Indeed, we haven't found any worlds that are square smack in the habitable zone where there's liquid water on the surface and other nice conditions.
Our frame of reference for what we consider to be a nice planet is this one. We like it quite a bit. We've got breathable air, it's a pleasant temperature, and there's water. And even in our own solar system, we don't see a lot of planets like that. And right now, the sort of planets we're discovering are kind of monsters. In other words, they're extremes.
So is the Earth, with its rocky surface, oceans, and abundant life, just a planetary wonder with no close kin in the cosmos? The early discoveries of alien planets have yet to answer that question. But they have brought legitimacy to what once seemed like a futile quest. While many believed there had to be other worlds out there in the vastness of the universe, locating them was widely considered beyond the reach of modern science. Only a few decades ago, an astronomer hunting for these so-called extrasolar planets was taken about as seriously as someone searching for UFOs.
The search for planets as it started in the 1980s and 1990s was considered off of the beaten track of standard science.
In the early 80s, astronomer Jeff Marcy's career was going nowhere. His research into the magnetic fields of stars had reached a dead end, and he was beginning to question his own abilities as a scientist.
When I first began thinking about looking for planets, it was in a time in my career when I thought it was over. I thought there was no hope for me as a scientist, and I thought the best shot I had going out in flames was to try an experiment that everybody thought would never work, namely looking for planets around other stars. And most people thought we would never find any planets.
Before Jeff Marcy, his collaborator Paul Butler, and a handful of pioneering astronomers around the globe could begin the search for alien planets, they had to first perfect methods for finding them. Stars are easy to locate using conventional telescopes, but to find a planet takes some ingenuity and patience. Unlike the stars they orbit, planets are small and emit very little light. Even the giant of our solar system, Jupiter, is 1,000 times less massive than the Sun and 10 billion times fainter.
A huge difficulty in taking a picture of a planet around a star is that the planet is extremely, extremely faint compared to the star. The star is so bright, it almost completely obscures the much, much dimmer planet.
Blinded by starlight, planet hunters realized that even if they couldn't see a planet directly, they should still be able to detect its gravitational effect on the star it orbits. A star with no planets should drift smoothly through the sky, while one with planets should exhibit a telltale gravitational wobble.
We often say that planets orbit the sun or other stars, but that's not exactly true. The planets and the stars orbit their common center of mass or center of gravity.
And this center of mass isn't halfway between them. Just like on a seesaw, the more massive object must be closer to the center of mass to bring balance to the system.
So consider the Sun and Jupiter. The Sun is about 1,000 times more massive than Jupiter. So the Sun is here, the fulcrum or balancing point is there, and Jupiter is way out here 1,000 times farther away.
In space, this means that planets trace out large orbits around the center of mass, while stars make much smaller but still detectable orbits.
Here's a hypothetical planet orbiting a star. In fact, they're orbiting their common center of mass. So the planet moves in a relatively large orbit, but the star also moves, but in a much smaller orbit. So the star moves only a little bit, and the planet moves a lot.
I have a somewhat unusual hobby for an astronomer. I'm a belly dancer and fire performer. But it turns out that spinning fire is a great way of simulating the motion of a planet. And the centripetal motion of your fire on a chain is very similar to the motion of a planet under gravity. The light on my wrist represents the star, and the spinning ball of fire around that is a planet. And as you can see, the ball of fire draws out a large circle, and my wrist is drawing out a smaller circle inside it.
It's this tiny wobble of starlight that scientists use to find extrasolar planets. But even this wobble would be undetectable if it wasn't for the Doppler effect, the fact that wavelengths get shorter as the object emitting them moves toward you and longer as it moves away from you.
The Doppler effect is very familiar if you've ever heard a train going by blowing its whistle. So when the train is coming toward you, you hear a high-pitched whistle. And as the train recedes into the distance away from you, you hear the pitch of the whistle get lower and lower in frequency.
Just like sound waves, light waves appear to shift in frequency as the object emitting them comes toward or away from you. Light from an object moving toward you will look slightly bluer. Light from an object moving away from you will look slightly redder.
When the light waves shift their wavelength toward the blue and toward the red and back toward the blue again as the star wobbles around, the shift is excruciatingly tiny. But it's that difference in the wavelength of the light waves coming at you that is what we measure, and it's what allows us to detect planets around other stars.
Using this Doppler technique, Marcy and Butler spent over a decade patiently studying 120 nearby stars for any sign of a wobble.
I went 11 years without finding a single planet, nothing. And no one was surprised by that. It seemed logical to everybody else that it was a fruitless, frivolous, maybe even lunatic exercise to look for planets of any sort.
But then, in 1995, came the surprise announcement from Swiss astronomers Michel Mayor and Didier Queloz that they had discovered a gas giant planet circling the star 51 Pegasi. Marcy and Butler rushed up to Lick Observatory on Northern California's Mount Hamilton to aim their own telescope at the star and see if they could confirm the Swiss team's results.
Yep, there it is. Looks beautiful. Paul Butler and I were shocked to see that the wobble of the star was precisely as the Swiss had said it was. And I remember driving off Mount Hamilton from Lick Observatory in complete silence, Paul Butler next to me. We knew that the first extrasolar planet had been discovered. It was a very moving, personally moving moment.
Despite the monumental nature of the discovery, this, like all future extrasolar planets, wouldn't get the name of a Greek or Roman god. It would take the astronomical catalog name of its parent star, 51 Pegasi, and add to it a lowercase b. In this standard nomenclature, if a second planet was found around the same star, it would get a lowercase c, and so on through the alphabet. Its name was the only thing unassuming about 51 Pegasi b. The discovery shook the foundations of our understanding of planets. In 1995, astrophysicist Alan Boss was asked to review a paper announcing the discovery by 2 Swiss astronomers of the first planet orbiting an alien sun.
Reviewing this paper caused me a fair number of sleepless nights because it was pretty stunning what they had found.
Stunning because the Swiss claimed to have found a Jupiter-like planet. But where Jupiter orbits the sun in 12 years, this planet zipped around its star in only 4 days.
And that also meant that the planet had to be much, much closer to its central star, roughly 100 times closer than Jupiter is. And that just was hard to understand.
Jupiter orbits the sun at a comfortable distance of around 500 million miles. 51 Pegasi b is more like 5 million miles from its star. If it were dropped into our own solar system, this alien planet would orbit much closer to the sun than Mercury, our innermost planet.
Being so close to the star means that the planet is being literally fried. The radiation from the star is incredible compared to what we experience here on Earth, relatively far from our sun. So this was a completely unexpected discovery.
It was a planet that could not have formed there. Astronomers knew it didn't belong there. In the same way that if we found a giant redwood in the middle of Central Park, we would know that it didn't belong there. You'd have to ask yourself, how did it get there? And that's what astronomers were asking themselves about these giant planets that they were finding.
51 Pegasi b wasn't just a freak of nature. It was the first of dozens of so-called roasters or hot Jupiters to be discovered in seemingly impossible close-in orbits. Impossible because the accepted theory for how gas planets form suggests that rock and ice in a disk surrounding a young star coalesces into a solid core that then accretes gas, growing larger and larger until it has cleared out all the planet-forming material in its area. This process can only occur at a distance far enough from the star where it's cold enough for ice to exist.
You can't form something that massive that close in to its star. It needs to form past the snow line where ice can form. And in our solar system, that's about where Jupiter is, about 5 times further out from the sun than the Earth.
So how could a gas giant planet like 51 Pegasi b form so scorchingly close to its star?
It was one of these things where I woke up in the middle of the night, and one night I said to myself, maybe what this means is that this object had to have migrated inwards from where it originally formed.
We now, I think, have an understanding that planet formation is an almost chaotic process, a sort of roll of the dice, with many planetesimals, wannabe planets forming, building up, and a competition, a sort of gravitational musical chairs takes place, in which the planets compete for their own space.
In this competition, some planets are flung out of the solar system, and some are tossed toward the center. It's believed some planets crash and burn on their parent star, while others survive in a close but stable orbit. These survivors are the hot Jupiters. The discovery of the hot Jupiter, circling 51 Pegasi, sent planet hunters Jeff Marcy and Paul Butler back to analyze the data they'd been collecting for the past decade. Their team had been looking for the expected long-term wobbles caused by a giant planet.
We ourselves suddenly realized we should analyze our data in a slightly different way, look for the shorter period planets, not just planets that take a long time to go around their star, and that led us to discover within existing data all of these planets that had been buried there for years. I remember the day like it was yesterday, December 30th, 1995, and at 8 a.m. the phone rings. I pick it up, it's Paul Butler, my ace collaborator for 20 years now. And Paul just said, "Jeff, come over here." So of course I immediately got in my car. I drove right to this very office right here where I'm sitting now in Campbell Hall at UC Berkeley. And he showed me his computer screen, and there on that screen was the unmistakable graph of the wobble of the star 70 Virginis, going up and down the star, wobbling to and fro, exactly as we had imagined a planet signature would look in our data. So that was the moment, with both of our eyes open this wide, that we knew we had discovered our first planet, the second planet ever discovered.
70 Virginis b is 59 light-years from Earth in the constellation Virgo. With a mass at least 7 times larger than Jupiter, this world immediately claimed the title as the planetary heavyweight of the known universe.
Here, right before our eyes, essentially, is a planet 7, maybe 10 times bigger than our own Jupiter, telling us immediately that, yes, nature does make planets even bigger than the largest ones we have here in the solar system.
Rather than a hot Jupiter, this planet was the first of a new class of alien worlds called eccentric giants, because of their eccentric or elongated orbits. 70 Virginis b swings out as far as 63 million miles from its star and passes as close as 27 million miles.
The frightening aspect of the planet around 70 Virginis is that we all grew up in kindergarten learning that planets go around the sun in nearly circular orbits. So what in the world is a planet doing going around its star in one of these elongated, wacky orbits?
Already, the first 2 planets discovered around alien suns were challenging our view of how planets should behave. Further discoveries over the next decade would show that eccentric orbits are common in the universe, while the circular orbits of our solar system seem to be rare.
It's embarrassing, frankly, when you think about how we humans imagined planets would orbit other stars, how common they would be, what properties they would have. Guess what? We imagined that those planets would look just like the planets that orbit our sun. Extraordinarily nearsighted in retrospect, and for a scientist, I find it embarrassing that I was party to this. But in fact, what we've learned is that planets around other stars are remarkably different from the representatives we have around our sun.
The planet-hunting revolution that began in the 1990s has also obliterated any notion that planets are rare in the universe. With an ever-growing catalog of alien planets, astronomers are now trying to learn all they can about the more than 200 worlds they've already discovered. The Doppler technique used by Jeff Marcy and other astronomers tells them the mass of the planet they found, but it doesn't tell them the size. To figure out just how big an alien planet is requires a bit of good luck. The orbit of the planet has to be aligned in such a way that from Earth, we can see it pass directly in front of its star. This is called transiting. By measuring how much the starlight dims during this transit, astronomers can actually determine the size of the planet. In the fall of 2007, astronomers were watching when a hot Jupiter called Trace 4 transited its star. The planet was about the same mass as Jupiter, and therefore should have been roughly the same size. But astronomers were in for a surprise. Trace 4 turned out to be almost twice as big as Jupiter. It was, in fact, the largest planet ever discovered, sort of a Jupiter on steroids.
Some of these extrasolar planets are really fluffy. They're really expanded in size. And we think that the reason why that's happening is because they have an internal source of heat, which is raising the pressure inside the planet and causing it to expand. That's very similar to a steam boiler on a steam train. In a steam boiler, you have water, which is being heated by a heat source. That water is turning to steam. The pressure is increasing, and that's causing the piston of the boiler to move out, to expand. If you didn't have the gas's ability to expand, the planets wouldn't inflate, steam trains wouldn't work, we wouldn't be climbing up this mountain.
While internal heating is the likely cause of the so-called fluffy Jupiters, something much stranger is happening on this alien world. In the field of extrasolar planets, it seems each new discovery creates a brand new world of scientific intrigue. At the University of Arizona, planetary scientist Adam Schoeman ponders the weather on other planets. Recently, Schoeman helped generate the first ever forecast for a planet beyond our solar system. And what he found was weather truly befitting an alien world.
We think that the winds are probably about 6,000 miles per hour, possibly even more. This is huge compared to the wind speed on any planet in our solar system.
This is HD 189733b. It's a hot Jupiter, more than 60 light years from Earth, that races around its sun-like star in a little over 2 days, at a distance of only 3 million miles. How is it possible to divine the weather on a planet 370 trillion miles away? First, you have to take the planet's temperature. Scientists knew that since the planet orbits so close to its star, it would be tidally locked, a gravitational effect that would cause it to show the same face to the star at all times. One side would always be bathed in the burning hot light of the alien sun, while the other would be cloaked in perpetual darkness.
If there was no wind on these planets, then that would mean that the day side would then be very, very hot, and the night side would be very, very cold.
In the spring of 2007, scientists used the Spitzer Space Telescope, which sees in infrared wavelengths associated with heat, to generate a crude map of the temperature on both the day and night side of the planet. You are actually looking at the first map of any kind made of an alien world. What the map shows is that the day side of the planet is roasting at an otherworldly 1,500 degrees Fahrenheit. No surprise, given how close the planet orbits to its star. What was surprising was how hot the night side of the planet turned out to be. Despite being in total darkness, it swelters at around 1,000 degrees. Clearly, something was distributing heat throughout the planet's atmosphere, carrying thermal energy from the day side clear around the other side of the planet. From his knowledge of weather in our own solar system, Schoeman knew what the culprit was. He ran the numbers, and that's when he figured out that this alien world had jet streams of unprecedented magnitude. Their 6,000-mile-per-hour winds dwarf anything in our own solar system.
Earth actually has the slowest speeds of any planet in our solar system, with a typical speed of about 20 miles per hour. The gas giants in our solar system actually have somewhat faster winds than the Earth, simply because there's no surface to have friction to slow down the winds. On Jupiter and Saturn, for example, the winds are a few hundred miles per hour. So they're still about almost a factor of 10 lower than on these hot Jupiters.
The weather on hot Jupiters may be extreme, but the forecast for another class of alien planets, the eccentric giants, is tailor-made for a disaster movie. This is HD 80606b, a gas giant planet located roughly 200 light-years from Earth, orbiting a star in the constellation Ursa Major. A year on this bizarre world lasts 111 days, and it has the most eccentric orbit of any known planet. With its nearly circular orbit, Earth's distance from the Sun changes relatively little throughout the year, varying by only about 4 million miles. But during its year, HD 80606b comes as close as 3 million miles to its Sun, and as far as 78 million, a difference of 75 million miles.
This crazy orbit leads to completely crazy weather. The planet heats up by hundreds and hundreds of degrees in a matter of a few hours, and that drives just absolutely tremendous storms.
As the planet swings in close to its star, the alien sun looms ever larger in the sky.
And so you get a huge amount of heating on one side of the planet. The other side of the planet is in the night. And what that does is it drives an intense storm. It's basically a shock wave around both sides of the planet that is moving roughly at the speed of a supersonic jet.
This fiery hurricane rips around the planet in only 12 hours. As the shock wave slowly dies down, the superheated atmosphere churns into a giant vortex that engulfs an entire hemisphere, a sort of greater red spot. As the planet moves away from the heat of its star, the storm gradually loses energy and intensity. But on this eccentric giant, the calm never lasts for long. Every 111 days, the shock wave is reignited and the violent cycle begins anew.
It's much stranger than anything that we have in our own solar system. If you were there, you would be incinerated immediately before you had a chance to really sort of groove on your surroundings.
The universe seems adept at creating strange worlds, even in the most unlikely of places. This is a pulsar, a rapidly spinning variety of an exotic stellar object called a neutron star. Neutron stars are the remnants left behind after a massive star explodes in a supernova. No one expected to find planets circling in such a treacherous cosmic neighborhood.
Never in my wildest dreams did I think we would ever find planets orbiting a neutron star, a pulsar. I mean, after all, neutron stars are formed as a result of supernova explosions where the star just blows up. So certainly any planets that might have been there to begin with would have been blown away.
And yet, in the early 1990s, astronomers discovered 2 rocky planets around a pulsar 7,000 trillion miles from Earth. Their discovery, in fact, predates 51 Pegasi b, making them technically the first alien worlds ever detected. But since they orbit such strange stars, many astronomers consider pulsar planets to be in a category of their own.
The pulsar planets were very interesting. They're actually very low in mass and more similar to the Earth's mass. They form an interesting exotic classification or family of planets, but it's by no means the mainstream.
While most planets are believed to have formed out of the same disk of gas and dust as their parent stars, clearly these pulsar planets formed a different way.
The planets that have been found must have formed after the supernova explosion. And that's really bizarre because we would think that all of the material was blown away, but apparently some of that debris must have somehow been in a disk, and parts of that disk coalesced into planets. But that's extremely surprising. I don't know that anyone really understands that process yet.
Although the pulsar planets are believed to have rocky surfaces, it's unlikely they would be a platform for life, and any visit by humans would be short-lived. As the pulsar rotates, it emits well-focused beams of charged particles from its poles, creating a rotating spotlight of horrific radiation.
Standing on a pulsar planet would be a very dangerous proposition. There would be high-energy radiation all around you, just an onslaught of particles and waves, and the radiation field would be so strong that it would probably destroy your living tissue, and it would certainly cause cancer and mutations very quickly, but it would probably kill you. If you were really unlucky, or lucky, I suppose, if you're going to die anyway, might as well die in a spectacular way, you would be in the beam of the pulsar. So every rotation, the beam would flash past you, and you would see this incredibly bright beacon, like a lighthouse really close to you, just flashing in your face. It would not be a very hospitable environment, no way.
While the pulsar planets might not be nice places to visit, they have taught us something fundamental about planet formation in the universe.
These planets, weird planets around a neutron star, have taught us that planetary formation appears to be relatively easy. Gravity appears to like to pull stuff together when there's enough stuff in a given region.
If nature is so good at making planets, even under difficult circumstances, then the odds are fairly high that the universe is full of planets, and that somewhere out there in the cosmos, other Earths are waiting to be discovered. But if that's the case, then where are the Earths? Why haven't we found them yet?
The first planets that were found in the late 1990s were massive planets, 300 times the mass of our Earth. And it's really not a surprise that we found the most massive ones first. Like the giant redwood trees behind me, they were the easiest to see from the enormous distances that we were looking. So when we find stars where we say, there's just one single massive planet, one giant redwood, that's almost certain to not be true. There's almost certainly a forest of planets and asteroids and comets also orbiting that star.
As astronomers continue to scrutinize alien solar systems, they are edging ever closer to finding Earth-like planets. This is Gliese 436b. It's a world roughly 20 times the mass of Earth, similar in mass and size to Neptune. It orbits a star 30 light-years away in the constellation Leo.
I'm so excited about Gliese 436, I'm almost jumping out of my clothes. It's the most important discovery since 51 Pegasi, maybe even more important.
What has Jeff Marcy so excited is that this planet was found to have a density of 2.1 grams per cubic centimeter.
What does that mean? It's a spectacular number because every school child knows that the density of water is 1 gram per cubic centimeter. And we also know that rocks that you pick up on the street, the density of our Earth, for example, as a rock, is about 5 grams per cubic centimeter. And therefore this planet, around 436, is composed of a mixture of rock and water.
A planet made of rock and water sounds tantalizingly Earth-like. But Gliese 436b has so much water, there would be no land masses exposed at all. And you wouldn't want to take a swim in the oceans of this watery alien world. There may be a layer of liquid water on the surface, but below that, things begin to get a little weird.
There's so much water that the sheer gravitational force of the water molecules pressing down toward the center will crush the water so tightly that the water molecules are almost touching each other. It's a very odd type of water. In fact, we call it ice, even though it's not cold, because the water molecules will be arranged in a structure like ice, but only due to its high pressure.
Clearly, Gliese 436b isn't quite an Earth-like planet. But what about this alien world? What would make an alien planet truly Earth-like? It should be made primarily of rock, with enough water for oceans, but not so much water that the land masses are completely submerged. It would also have to be in its star's habitable zone.
The typical idea for a habitable zone is the range of distances from a star where an Earth-like planet could have liquid water at its surface. The idea would be that if you took Earth and pushed it in too far, the oceans would all boil away, and that's bad for life. Or if you took the Earth and pushed it out too far, the oceans would all freeze, and that's bad for life.
In our own solar system, the habitable zone ranges from Mars's orbit into as close as where Venus orbits. But the habitable zone in alien solar systems varies, depending on how hot the star is. Currently, our best hope for finding habitable Earth-like planets is to look around cool, dim stars called red dwarfs or M dwarfs.
The M dwarfs themselves are very special stars. So our sun might be a 100-watt light bulb. An M dwarf is perhaps a 10-watt light bulb. And so what that means is that to stay warm enough so that you have liquid water, not ice, but still not too hot, you move the planet in much closer. And those close planets are easier for us to detect with our technique because they tug on the star more.
One of these M dwarfs, called Gliese 876, has been found to have at least 3 planets orbiting it. 2 of them are gas giants, but the third, Gliese 876d, is one of the smallest planets discovered so far, at roughly 6 or 7 times the mass of the Earth. It's also just on the edge of its star's habitable zone.
The planet orbits in just 1.9 days around its host star, but because the host star is so low in luminosity, it puts it on the edge of what you might imagine the habitable zone to be. There could be some region, a ring around the planet towards the back side, where the temperature is actually just right for liquid water to exist.
When it was first discovered, scientists hailed this planet as the first of the super Earths.
7 times the mass of the Earth sounds so close to the size of our Earth that you wonder whether or not it's a rocky planet, maybe with a thick atmosphere.
But today, the experts are unsure whether this is a large rocky planet at all. Like Gliese 436b, it may be completely covered in an ocean of super dense water.
Well, to call it a super Earth is to suggest that we've found a planet that's a close cousin of our Earth. I would now rather think of it as a distant cousin, not unrelated to our Earth, but far enough away, indeed more like Neptune in our own solar system, that has a big rocky core, but surrounded by a big envelope of water.
So the race continues to discover the first truly Earth-like planet. At the University of Arizona, astronomer Laird Close is hoping to capture the first picture of an alien Earth. But to do that will take a giant leap in telescope technology. Here at the Steward Observatory Mirror Lab, in a cavernous space underneath the bleachers of the university's football stadium, engineers are working on the next generation of super telescopes.
This is the largest mirror that's ever been made. This mirror is 8.4 meters across, but it's just 1/7 of the size that's needed for the giant Magellan telescope. And together, when combined with 7 other mirrors like it for the giant Magellan telescope, we will be able to actually directly image extrasolar planets and maybe even Earth-like planets around alien suns.
Scheduled for completion in 2016, this telescope will be able to make images up to 10 times sharper than the Hubble Space Telescope. NASA and the European Space Agency are also developing several missions that will use space-based telescopes to search the stars for our planetary kin.
This will be incredibly exciting for humankind to know whether or not around those little points of light that we see in the night sky, whether there's Earth-like planets tied in orbit around those stars. As technology improves, we're going to be able to find planets that look much more like the Earth. Planets that perhaps have life on them, and maybe even planets that have forests and steam trains.
The astronomers who have dedicated their lives to this quest all believe it's only a matter of time before we find the first truly Earth-like planet.
The most exciting thing I can tell you is that we are now routinely commonly discovering planets that are a mere 5 or 10 times the mass of our Earth. We're not quite to the point where we're finding Earths, and that's where we really want to be. But we're finding planets that are ever so close to our home planet.
So when we actually do cross that final threshold and do find evidence that there's a habitable planet out there, this is going to be quite an epical event for humanity.
People should not worry too much yet that we haven't found any Earth-like planets because, well, a lot of effort's going into it right now, and I think it will be done in the next 10 years. Yeah, stay tuned.
In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
Lurking in the shadows of the solar system are worlds so chemically active and misshapen that they border on the bizarre.
I think the most shocking thing was how very different the solar system is.
These are the moons surrounding the planets of the solar system. Moons that were once either unknown or considered afterthoughts are now on the cutting edge of astronomical exploration.
What was surprising, that they all didn't look like our moon. The so-called minor members of the solar system are not of minor interest.
What surprises await us on these alien moons? Our solar system has always been fertile ground for science fiction writers. But with exponential advances in telescopic technology and close encounters by unmanned probes, the curtain has now been lifted on a new ballet of moons.
Most of which are going one way around, some of which are going the other way around, all at different rates, passing one another, the inner ones passing the outer ones.
For nearly half a century, it was believed the solar system was home to only 32 moons. They ranged in size from Jupiter's moon, Ganymede, larger than the planet Mercury, to small asteroid-shaped ones like the Martian moons, Phobos and Deimos. That number has exploded. In 2007 alone, scientists announced the discovery of 20 new moons around Jupiter, 1 around Saturn, and 3 around Neptune.
What happened is astronomical telescopes had available to them what are called CCD cameras. So these are digital cameras that almost everybody has nowadays.
It's difficult to hold astronomers to an exact number of moons in the solar system. As cameras become more sensitive and telescopes more powerful, more moons reveal themselves. Moons are classified in two distinct ways. Those, like our moon, travel in nearly circular orbits above their planet's equators and are called regular moons. While our moon formed from an impact, all other regular moons coalesced from the gaseous stew surrounding their parent planets, a process known as accretion.
The classic example of regular moons would be the Galilean moons of Jupiter: Io, Europa, Ganymede, and Callisto. The material that is going to form Jupiter too, but extended a little bit, that material accumulates into the moons.
Moons that follow elongated orbits, highly tilted to their planet's equators, are called irregular moons. Most of these move in retrograde orbits, clockwise if their planet rotates counterclockwise. Phoebe, the newly discovered moon orbiting Saturn, is a perfect example. She began her celestial life as an independent traveler, orbiting the Sun before being captured by the more massive Saturn. Whether regular or irregular, moons must fall within the gravitational reach of their parent planet. The limit of these orbits is known as the heliosphere. This phenomenon is named after George William Hill, an American astronomer from the mid-1800s.
So a heliosphere is this region around the planet that moves along with the planet, inside of which the gravity of the planet overwhelms the gravity of the Sun.
The moons of Mars, Deimos and Phobos, operate very differently within the heliosphere.
If the planet is rotating faster than the moon it orbits, like Deimos, the tidal forces between the two actually shove Deimos out further and further. Phobos, on the other hand, is rotating faster than Mars rotates.
These small moons were discovered by American astronomer Asaph Hall in 1877. He named Phobos after the Greek god of fear and Deimos for the god of terror. Tom Duxbury was part of the Mariner 9 mission that first photographed the two potato-shaped moons in November of 1971.
This was late at night in a cold, rainy, dark, dreary day, and I looked at this and I turned the picture sideways. It looked like a skull. And it was such an eerie thing.
Phobos is in a death spiral. It orbits just 3,700 miles from the Martian surface, closer to its host planet than any moon in our solar system. If our own moon were as close to the Earth as Phobos is to Mars, it would look 20 times larger.
Its orbital period would be in hours, not days like it is now, but hours. And at full moon, it would fill the sky.
The daily tides, would rise and fall tens of feet, if not hundreds of feet. And so the Earth's moon would eventually crash into the Earth in such a situation.
Phobos's predicament is caused by a process known as secular acceleration. As Phobos races faster than Mars rotates, a tidal bump is raised on the Martian surface. In the process, Mars yanks Phobos closer to its surface with each orbit. The struggle between Mars and Phobos is similar to the dynamics of a simple game of tetherball. Imagine the ball as the moon, the pole as the planet, and the rope between the pole and the ball as the planet's gravitational pull.
What we see is that the gravity would pull the moon in such a way that it speeds up. It goes faster and faster, and it works its way until it eventually hits the pole. That's exactly what's happening to Phobos. Phobos is going around Mars faster than Mars rotates. that tidal interaction is pulling Phobos in closer and closer and speeding it up in its orbit. In about 50 million years, we expect Phobos to be pulled in so closely it will impact Mars and disappear as the moon of Mars. On the other hand, Deimos, the further out moon, is going slower than Mars rotates. And so it's unwinding the string in the opposite way. And what we see is Deimos is going further and further away from Mars. And eventually Deimos will be pulled away from Mars by the gravity of the sun. So over time, Mars will become moonless.
Because Phobos outpaces the rotation of Mars, it appears to rise in the west and set in the east.
Instead of the planet turning quickly under it like our moon and most other moons, and thus having it rise in the east and set in the west, it races ahead of the rotation of the planet, and so it comes up on the western horizon and races ahead and sets on the eastern horizon.
It will be another 50 million years before Phobos completely disappears. Before then, it may prove useful for the eventual colonization of Mars. Science fiction writer Arthur C. Clarke speculated on this idea in his book, The Sands of Mars. Although there is no real reason to colonize Phobos itself, its close proximity to Mars makes it a natural way station.
From a gravity standpoint, it's much easier to go to Phobos, which has no gravity, than it is to fight the gravity of Mars to get down to its surface.
From Galileo to Stanley Kubrick, the giant planets of the outer solar system have tantalized our imagination with their enormity. But in reality, exploring them is tantamount to suicide. The overwhelming pressure from Jupiter's massive atmosphere would make it almost impossible to function. But the moons of these behemoths may provide a more promising platform for exploration and even future colonization. Are these prisoners of Jupiter's gravity, hostile worlds with little chance of sustaining organic life? Or might they provide a safe haven for future generations of planetary explorers? Until recently, very little was known about the moons of the gas and ice giants. Most of them remained hidden in the glare of their parent planets. Today, modern telescopes and unmanned space exploration reveal a realm populated by a host of moons, from planet-like spherical worlds to misshapen ones barely 30 miles across. Jupiter, the largest planet in the solar system, is a moon magnet. Nearly 4.5 billion years ago, it began as a massive gas cloud collapsing in on itself. This process, known as accretion, formed the beginnings of the Jovian system. While nearly all the gas and spinning material went into forming Jupiter itself, a very small percentage clumped in small eddies within Jupiter's orbit. These miniature accretions solidified into Jupiter's regular moons, Io, Europa, Ganymede, and Callisto. As Jupiter coalesced, its massive gravity began adding to its menagerie, little remaining bits from the birth of the early solar system.
The giant planets formed early in a gas-rich environment when there was lots of little flotsam and jetsam around the solar system still to be captured into orbit.
The number of Jupiter's moons ranges from 60 to over 200, depending on who's counting. What's clear is, if you could stand at the edge of Jupiter's gaseous atmosphere and look to the heavens, you'd see a magnificent dance of lunar objects.
It would look pretty cool to be able to see the moons. Every so often you'd see Io come by. Every second time Io comes by, you'd see Europa at the same time. And every 4 times Io comes by, you'd see Ganymede.
One member of this Jovian cast is so battered by Jupiter's great mass that it's literally bursting from the inside out. In February of 2007, the New Horizons spacecraft, eventually bound for Pluto, focused its cameras on Io. About the size of Earth's moon, it orbits 263,000 miles from Jupiter's surface. What sets Io apart from the other Jovian moons is its spectacular volcanism. New Horizons cameras captured detailed photos of glowing lava scattered across Io's surface. A huge 200-mile-high dust plume rose above the surface of the molten moon. Io, like all Jupiter's regular moons, is named after a lover of the god Jupiter from Roman mythology. It was discovered by Galileo in 1610, first photographed by Pioneer 1 in 1974, and again by Voyager 1 in 1979. Its pulsating activity has puzzled and intrigued scientists for decades.
Leaving Io is about a ton per second of material. Every second of every day. It's a phenomenal machine.
I would like to go to Io, even though it would be very dangerous and hot and sulfurous.
Io is too small to have maintained a molten core since its formation. Another mysterious process must be responsible for its heating.
Io's entire interior may be molten because it's squeezed so much as it's orbiting around Jupiter.
This process is known as tidal heating. The massive gravity of Jupiter is causing friction at the inner core of Io. Much like a sculptor needs a cold lump of clay, Jupiter is endlessly creating its own masterpiece.
If a moon gets a little bit of tidal heating, it becomes malleable. It can be stretched out like clay and deformed by the gravity of the parent planet. The surface of the moon is cold. It breaks, like pulling clay apart quickly. It'll break. But the interior, where it's warm, can literally flow and stretch and be kneaded by the gravity of the parent planet.
Most regular moons have circular orbits. To produce tidal heating, a moon must be in a more oblong orbit, where the distance from the host planet changes radically during a single revolution. The only way to produce these eccentric orbits is if another moon's gravity disrupts it.
When a moon is in an eccentric orbit, a non-round orbit, it gets closer and farther from its parent planet. When it does, it gets squeezed, it gets pulled apart when it's closer.
Io is in orbital resonance with its companion moons Europa and Ganymede. While Jupiter and Io struggle to find a synchronistic relationship, Europa and Ganymede are yanking Io in opposite directions. Jupiter yanks back, and Io gets stretched and squeezed in the process. The tidal heating on Io, which is responsible for its prodigious volcanoes, has a secondary side effect. It creates the largest stationary visible object in the solar system, a massive gas cloud 500 times the size of Jupiter. In 1990, Professor Michael Mandillo and his team from Boston University discovered a large gas cloud spanning the huge distance from one side of Jupiter to the other. They were the first to photograph the entire nebula, discover its origins, and the mechanism that keeps it growing.
Now, Io is small, so it doesn't have much of an atmosphere. But these volcanoes are continually providing material that could be an atmosphere. But you might ask, well, why isn't have a tremendous atmosphere if all the volcanoes have been going on for eons? Well, it's because the material escapes.
The key gas is sodium. Even though it only makes up 5% of Io's ejected materials, it's easily detectable by telescopes on Earth. Sodium emits an orange glow. In fact, sodium is commonly used to illuminate streetlights in many cities across the world. The sodium and the other gas molecules are pelted by light from the sun and electrons in Jupiter's powerful magnetic field. Electrons and protons are knocked off some of these particles and ionized. Now in plasma form, these ions are taken on a ride by Jupiter's powerful magnetosphere. Its speed increases dramatically because it's been picked up by the magnetic field. It's like they're taking a ride on a cosmic carousel.
The magnetic field lines are the poles here, and then every now and then, a sodium atom gets picked up along with its an electron. And now I'm in the Jupiter plasma torus with all the other ions and electrons that have been captured previously. And the ions and the electrons recombine, the neutral is not confined by the magnetic field, and it goes off at a much higher speed. And that's enough to escape from Jupiter. And they form the largest visible cloud of gas that's permanently in the solar system.
If we could see the nebula with the naked eye, it would be the size of 12 moons in the night sky. It is so enormous that to view it, Mendillo and his team created their own specialized telescope.
Well, as it turns out, to get a big field of view, all you need is a small lens. Like a pair of binoculars gives you a big field of view.
Even in 1991, the telescope may have seemed ordinary, but its camera was highly sophisticated and, at the time, revolutionary. The digital camera.
Well, once you've got a picture that's in numbers, you can do all kinds of things with it.
Mendillo and his team knew that sodium existed in the nebula. Sodium also exists in the Earth's atmosphere. They were able to compare digital photographs of both Jupiter and Earth's atmospheres and bring forth an image of the nebula.
Well, that was very difficult to do if you just had two photographs and pieces of paper. But now that we have these digital cameras, we've revolutionized the way that we can process images.
Though Io would be a fascinating scientific and aesthetic destination, its hostile environment probably precludes that. Even landing an unmanned probe would be difficult among Io's convulsing fissures. But there's another moon orbiting Jupiter which may not only support human exploration, but possibly support its own alien life forms.
Europa is one of the most fascinating and enigmatic objects in our solar system. Really unlike any place else in the solar system, and for that matter, unlike anything on Earth.
The surface features are such that there are cracks in the surface, there's mottled terrain, there's chaotic terrain, and it looks like icebergs in some areas.
We know Europa is an alien moon. Could it be home to alien life forms as well? Europa orbits 400,000 miles from Jupiter's surface, about double the distance of Io. And like its convulsive cousin, it too is molded by gravitational tides. Jupiter has the greatest effect. Its mass, like a persistent lover, pulls the reluctant moon toward its surface. Europa resists with its own gravity, and they form a kind of symbiosis, hundreds of thousands of miles above the gas giant. But it's not just Jupiter tugging at Europa. Little Io and larger cousin Ganymede pull at Europa from different directions. It's the same orbital resonance that has such a dramatic effect on Io. However, the results are far different on Europa. Europa's surface is cold, minus 550 degrees Fahrenheit in some places. Yet there is heating. And what rises to the surface of Europa is also what makes the moon so exciting. Water. This water, actually a kind of glacial ice, is rising from an underground ocean and oozing out onto the surface, repaving it as a Zamboni does an ice rink.
Europa's ocean is thought to be shallow, only about 10 or 15 miles below the surface.
Water was the cradle of life on Earth. Could the same be true on Europa or other moons?
Icy satellite oceans could be the most common habitat that exists in the universe. Earth's might be relatively rare, but icy satellites are probably plentiful.
In February of 2007, the New Horizons spacecraft, on its way to Pluto and the outer reaches of the solar system, managed to fly close enough to Europa to send back some startling pictures. Seen only as the sun is rising or setting behind Europa are enormous geological patterns that have been dubbed crop circles.
They are very large. If you were to, try to drive across one of the circles, you would very, gently go in and travel down to a location that's a few hundred feet lower than the surface you came up from, and then rise back up.
The resemblance of Europa's crop circles to the mysterious ones that dot the countryside here on Earth ends when you consider their size. Each one is 2,000 to 3,000 miles in diameter. They're too shallow and uniform to be impact craters. Asteroids and comets come in different sizes and shapes. Europa's crop circles are remarkably similar geologically. Although nothing has been proven, it seems the great mass of Jupiter may once again be the culprit. The speculation is that the icy covering surrounding Europa is not tethered to the core of the Moon. Rather, it's floating above the subsurface ocean, like a spherical iceberg. The polar region may be somehow shaped by Jupiter, and then over hundreds of thousands of years, slowly tugged toward the equator. This forms a line of small circle depressions dropping from the polar region toward the equator. If Europa's ice crust has similar structure to icebergs on Earth, most of it would be under the ocean's surface. This has huge implications for future exploration.
It means there has to be something like 8 or 9 times that amount of ice underneath them to allow that kind of large-scale topography to exist.
The iceberg theory lays to rest the belief that Europa's subsurface ocean can be easily tapped through a thin crust. Radar mapping and ultraviolet data will prove to be even more important before a Europa lander can make its way down to the surface. Future explorers will have to search out hotspots and places where this mysterious ocean has welled up through the surface, and from there try to find a way to dip into it. Those explorers may choose instead to set up a base of operations on Ganymede, Jupiter's largest moon. As Phobos might serve Martian exploration as a way station, Ganymede might do the same for the Jovian system. Larger than the planet Mercury, its gravity is closer to that of Earth's than any of Jupiter's moons. And though it's in orbital resonance with both Io and Europa, it's far enough away from Jupiter to be less affected by the gas giant's relentless tides.
And at Ganymede, you could say, park in some nice big crater and build your domed, protected region, protected from the charged particles in the Jovian system, and make a pretty safe place to study not just Ganymede itself and its magnetic field and its interior and its geology, but the Jupiter system as a whole.
Ganymede is the only moon in the solar system with its own magnetic field. To have this distinction, Ganymede must have sufficient mass and a hot inner core. Its mass is obvious, but where the heat is coming from is a bit of a mystery. Ganymede is affected by both Io and Europa's tidal forces, but measurements on its orbit indicate that it's round enough to avoid the squashing and stretching that its smaller cousins endure from Jupiter.
The thought is maybe something happened in Ganymede's past to change its orbit slightly, and maybe its eccentricity got kind of haywire for a little while and generated a lot of heat within Ganymede, caused the core to be hot. We don't really know.
What we do know is that New Horizons' recent flyby of the Jovian system gave us a tantalizing glimpse at the wonders that await us on Jupiter's alien moons. Scientists look forward to the day a lander touches down on one of these moons and starts to uncover the secrets of these mysterious worlds. A Another icy moon orbits the gas giant Saturn. It's too small to hold on to its own atmosphere, but that doesn't stop it from sapping the atmosphere of its parent planet. Enceladus, even though quite small, is named after a tribe of giants in Greek mythology. Like Io and Europa, Enceladus has an eccentric orbit around its parent planet, Saturn. The tidal forces of Saturn squeeze and knead this tiny moon and create heat at its core. But unlike Io, it doesn't regurgitate molten material that coalesces into a massive gas cloud. Water doesn't well up to the surface as it does on icy Europa. No, Enceladus actually spits plumes of icy water into the atmosphere of Saturn.
So we don't call it a volcano, it's more like a geyser. The water vapor is then in orbit around the little tiny moon, or because it's near Saturn, Saturn's gravity can pull it into the planet.
Interested by their work on the torus of Io, Michael Mandillo and his team at Boston University began to consider Enceladus's effect on Saturn's atmosphere.
And it turns out that water is a wonderful catalyst to have the ions and electrons recombine.
Before Cassini, scientists relied on computer models to determine atmospheric conditions surrounding Saturn. They indicated that Saturn should have a very robust ionosphere. Surprisingly, Cassini's data indicated that Saturn's ionosphere was only 10% of what computer models had predicted. It seems that the icy water ejected from Enceladus is neutralizing the charged particles in Saturn's ionosphere.
Commit. Liftoff.
Scientists had learned, quite by accident, the effect water can have on Earth's atmosphere.
In 1973, when NASA launched its Skylab workshop, it launched its last gigantic Saturn V rocket, the moon rocket. And it had never had a launch that allowed the space vehicle to keep its engine burning as high as the ionosphere. Well, this gigantic engine dumped a ton per second of water vapor, which comes out of a giant rocket motor, into the ionosphere. And the ionosphere nearly vanished on that day.
It blew a gaping hole in Earth's ionosphere, the top layer of the atmosphere. A hole that took the sun's ionizing radiation 24 hours to repair. However, on Saturn, where Enceladus continuously dumps 6 tons of water per minute into its atmosphere, the long-term effects have been significant. There's no worry that Enceladus will strip away its parent planet's ionosphere completely, but this tiny moon, only 300 miles in diameter, has gotten the attention of the scientific community and Saturn itself. While we prepare probes to Phobos and Europa and study data from Enceladus and Io, an entirely new set of moons has literally just come into the picture. Before the 1990s, most astronomers agreed that there were only 34 moons in the solar system. Most of those were regular moons like our own, spherical bodies that orbit their host planet in the same direction it rotates. But a handful of these satellites were what's known as irregular moons. These freakish moons follow elongated orbits. Their orbits are often tilted, and they rotate in the opposite direction of their host planets.
They look like flying potatoes or splinters or misshapen lumps.
They've been hard to find before now because they're very small and they're also usually very dark.
The advent of digital photography and the use of light-sensitive optics changed the lunar terrain within a decade. Dr. Brett Gladman from the University of British Columbia discovered his first irregular moon in 1997 at the Palomar Observatory. Since then, Dr. Gladman has brought to light 17 previously hidden objects in the solar system.
So you detect objects in the outer solar system by observing them move relative to the background stars and galaxies, which are stationary. So if you take a picture of the sky and you wait an hour and you take another picture of the sky, none of the stars and the galaxies will have moved, but distant objects in the outer solar system will displace by a visible amount between the two pictures. And so by comparing the two pictures, you can see, as we have here, a moving target.
The object could be a comet or an asteroid, or, if it orbits a planet in a retrograde fashion, a new irregular moon. Another important distinction between regular moons and their irregular counterparts. Irregular moons are captured. That is, they formed independently of their host planet and most likely were part of the debris that originally formed our solar system. Phoebe, the largest irregular moon orbiting Saturn, is a classic example.
Phoebe orbits Saturn very far out. It has a very elliptical and very inclined orbit. It orbits in a retrograde direction. Voyager images suggested that this thing looks like it could be an asteroid, and so people thought maybe it is a captured asteroid. Now we know from Cassini it's a very water ice rich body. That pretty much rules out the asteroid belt. The thinking is that Phoebe could very well have come from the Kuiper belt, way out in the outer reaches of the solar system.
The Kuiper belt is thought to be the debris left over after the solar system formed. It revolves around the sun beyond the orbit of Pluto. However, another theory suggests something altogether different.
It's much more likely that Phoebe formed in an independent orbit around the Sun and then was captured into orbit around Saturn, whereas most of the other objects that formed near Saturn's distance were either accreted by Saturn or ejected from the solar system.
Phoebe would then be made of the planetary debris that was floating around Saturn at the time of its birth. And possibly it's made up of different material than some of the irregular moons orbiting Jupiter. If this is the case, astrogeologists may be able to discern and compare the different ingredients that birthed these two gas giants. Three main theories currently exist as to how Phoebe and its other irregular counterparts lost their independence. Two suggest the irregulars were captured as the solar system was still forming and the planets were still an accreting blob of gas and debris. The gas drag theory is the most straightforward. Thick gases were swirling around the accreting planet when a comet, asteroid, or a shattered combination of both passed through the gaseous mixture.
We know that the giant planets built their regular satellite systems in a large accretion disk around each of the planets, sort of like a mini little solar system forming around each planet. And the gas and dust that was in that disk can also serve in its outer regions as a source of friction where passing planetesimals formed independently are slowed down a little bit and captured into orbit.
The second theory is really a variation on the first. It's sometimes called the pull-down theory. Here, instead of an object being caught by simply passing through the accreting gases, it is unsuspectingly pulled into the forming planet's orbit by its growing gravitational pull. The gas drag and pull-down theories of capture work well for both Jupiter and Saturn because their mixture of ingredients was massive enough to slow down these passing objects. But what about the icy giants, Neptune and Uranus? Because of the extreme cold, they formed much more slowly, and it's difficult to believe that their icy accretion mixture contained enough mass to snare a passing piece of the solar system. Yet both icy giants have their own irregular moons. Hence a third theory, three-body interaction.
You discover that many of the objects are actually more than one object. They're usually two objects often, that because they're both more or less the same size as the other in a binary relationship, instead of being a big object with a small object going in orbit around it like this, it's two more or less similar sized objects going around a common orbit. Between the two of them is called the barycenter.
A binary pair exists when two objects of the same size are tight enough to the barycenter to prevent a third larger object from splitting them apart. But when one of the binary pair is significantly larger than the other, the more massive third object has a greater chance of separating them.
the smaller one will tend to have the much bigger orbit, swing out further.
This brings the smaller object close enough to the planet to be captured, while its partner is slung out into an independent orbit. One bizarre moon seems to defy classification. Triton orbits Neptune in a retrograde fashion, counter to Neptune's rotation. That would make it an irregular moon, except that it's spherical and orbits close to the equator, with an almost perfectly round circumference, a classical description of a regular moon. It also spews out mysterious icy plumes, with some indications that it once was, or possibly still is, volcanically active. Before Voyager 2 ventured into the outer solar system, Neptune's moon Triton was assumed to be a geologically dead ball of rock about the size of our own moon. When Voyager beamed back photographs revealing a world with mountains, fault lines, and fissures indicative of tectonic movement, as well as a surprisingly thick atmosphere, scientists were amazed. Geologic forces, usually associated with much warmer and larger planets, might be occurring on a frozen moon slightly smaller than our own. Voyager detected no active volcanoes in 1989. However, like Saturn's moon Enceladus, geysers periodically erupted from the planet's surface. What's really stunning about Triton is not just that it has some unique geological processes occurring, but the fact that they're happening even though Triton is an irregular moon.
Most large moons in the solar system are regular satellites, with the very important exception of Triton, Neptune's largest moon, which orbits the wrong way. So Triton is thought to have been a captured object.
A captured moon that acts like a regular one. How did an object the size of Triton slow down enough not to either pass through Neptune's atmosphere or collide directly into the icy planet? There's no sure bet, but some theories carry better odds. Much like gamblers at the roulette wheel, Triton and Neptune played the odds and trusted to luck.
Place your bets, get lucky now.
In roulette, there are several ways to bet. Each one carries different odds, and like most games of chance, the longer the odds, the greater the payoff.
20 black, 20 black, even.
There are at least 3 possible ways Triton could have been captured by Neptune.
All 3 hypotheses are physically possible, but the first one, the idea of gas drag, is the least likely simply because the period of time in which Neptune had a disk of gas and dust which could have captured a proto-Triton object was a very short period of time, and so the window of opportunity was very small. So that's like betting on the green 0 on the roulette table. More likely is the possibility that the proto-Triton sometime in solar system history crashed into a set of regular middle-sized icy satellites, and it was the collision which gave us Triton. And that's like betting on the first third of the numbers on the roulette table, so you have like a 1 in 3 chance of that taking place. Your best bet is to bet on the even numbers. There you have a 1 in 2 chance of things happening, and the best bet for the capture of Triton right now is this binary capture hypothesis, because there we know there are probably thousands of objects that have existed in the Kuiper belt that would have the right size and be partnered with another even larger object, and Neptune could capture one of them.
No one knows for sure which number paid in the early days of the solar system when Neptune captured Triton. However, once Triton began orbiting Neptune in an irregular fashion, it started obliterating anything that got in its way.
Neptune doesn't have a very regular system of satellites. It's thought that the capture of Triton disrupted what would have otherwise been a nice regular system like the other large planets have.
It's as if Triton was angry at losing its freedom and took it out on Neptune's other hapless moons. But where did this headstrong moon come from? Data from Voyager 2 indicates that Triton's density nearly matches Pluto's. This suggests a kinship that no other regular moon can claim. It's suspected that Pluto and Triton are both objects that originated in the Kuiper Belt.
The outer solar system consisted of these large objects going every which way, essentially. Some of them formed giant planets themselves, and some of them were tossed out further, where they sit today in the Kuiper Belt.
Collisions, accretions, and even captures have diminished what was once a major thoroughfare of planetary building materials.
Early in solar system history, the Kuiper Belt had far more larger objects that may have once had a cumulative mass of 50 Earths, whereas the current Kuiper Belt mass is much less than 1 Earth.
What's left of the Kuiper Belt is as old as the solar system itself. The material that makes up the binary objects, shards of collisions, and even some alien moons hasn't changed in over 4 billion years.
It's amazing how really different all the moons of the outer solar system are. When I first got interested in astronomy as a kid in the 1960s, we hadn't seen any of these moons. They were little dots in your telescope, and so we had no idea how radically different they could be. I think the most shocking thing was how much variety there is in the solar system. I think that blew me and everybody else away who lived through that period.
As we travel back home from the frigid outskirts of our solar system, awed by the vastness of the universe and the majesty of the planets, it's worth it to pause and take notice of the small worlds in the shadows. Those alien moons that were once considered afterthoughts hold mysteries just waiting for human curiosity to solve. In the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the Univers. In the deep nothingness of space, the cosmic silence is broken.
Space is actually kind of a noisy place.
Galaxies, stars, planets, and moons sing out with strange and alien music.
They sound a little bit like an alien fax.
Now, the cosmic playlist in a top 10 countdown. The greatest hits of the universe in a symphony of alien sounds. In space, no one can hear you scream. As the promo line for Ridley Scott's science fiction film Alien, it was designed to send chills down your spine. It's based on the unsettling idea that space is a vacuum, and sounds, whether screams, shouts, or songs, can't travel in a vacuum. But is that really true?
Well, it's kind of narrow to think that in space you can't hear anyone scream, because in fact, here on Earth, there are lots of sounds we can't hear. They're either too high a pitch or too low a pitch. Moreover, space isn't completely empty. And then finally, what's the definition of space? If I'm an astronaut on the surface of Mars and I have a spacesuit on, am I in space or am I not? Well, I would think I am.
Okay, let's try right over here.
Back on Earth, Bruce Betts of the Planetary Society in Pasadena, California, has given a lot of thought to Mars and the subject of sound. He's programmed his computer with what he calls the Marsinator to demonstrate what his voice would sound like in the cold carbon dioxide atmosphere of Mars without those spacesuits.
The atmosphere of Mars would actually change your voice so it sounded deeper.
So let's go ahead and simulate that using the Marsinator. And I will record my voice, and then we will shift it to what it would sound like on Mars. This is what I'd sound like on Mars, although I'd be wishing I had some oxygen to breathe. Then I go ahead and process it, put it through the Marsinator, and then we play it back and see what it sounds like.
This is how I would sound on Mars, although I'd be wishing I had some oxygen to breathe.
Of course, if humans ever do make it to Mars, we will not hear their voices through the atmosphere. Instead, we'll get them via radio waves, the way many of our most important sounds already reach us.
Yes. We're familiar with thinking of sound as something that comes through the air to us, just like we hear each other when we're talking. But in fact, a lot of the sounds that we hear are transmitted through electromagnetic signals. For example, your television actually transmits a television signal into sound that you can hear.
Who's our first contestant tonight?
Sound in the cosmos will never reach us directly across empty space. So radio, light, or other electromagnetic waves are the inevitable carriers, bringing us a universe we can hear in all its variety.
Space is actually kind of a noisy place. It has many, many sources of noise that we are able to detect with special radio telescopes, for example.
These alien sounds make up an incredible collection, the ultimate playlist. We've polled our expert panel of scientists, astronomers, and physicists to rank the top 10. The greatest sounds from the expanse of space, ending with a number 1 that will surprise us all. And now the countdown starts. Coming in at number 10, ringing out from a distance of 13 billion light years, the birth cry of the universe in a hit called The Audio Afterglow of the Big Bang.
It's remarkable that the young universe actually made a sound, and the reason we know that is that we can actually witness the glowing gases that were present at that time.
The glow from these gases is known as the cosmic microwave background radiation, or CMBR. It is a faint trace of microwaves that stretches across every point in the sky. Discovered by scientists in the mid-1960s, the radiation is the afterglow of the Big Bang. The famous blotchy satellite map of the CMBR represents the cosmos in its infancy, when it was only 380,000 years old.
When we look at the CMBR map, we're essentially looking at a voice print of the early universe, because those tiny variations in color correspond to variations in temperature, and those correspond to variations in density and pressure. Well, pressure waves are just sound waves, so we're seeing little variations in pressure, little sound waves in the early universe.
To understand the audio afterglow of the Big Bang, we need to know how the early universe varied its pressures to generate sound waves. To find out, astronomer Mark Whittle and organ builder Manuel Rosales visit the magnificent pipe organ at Claremont United Church of Christ in California. In a way, the 4,000 pipes in this organ are comparable to the voice of the early universe.
Manuel, the amazing thing about the early universe is that all its pipes were sounding together. And it'd be lovely if we could just try that with this organ. So do you think we could do that now, play all the notes at once?
Yes. Let's pull out all the stops and try it.
Ah, that's where that phrase comes from.
Yes.
Okay, let's go. Very powerful, but really hissy, white noise kind of sound. But an even more remarkable thing about the primordial sound is that, in fact, a few particular tones were present and were stronger at any given time.
This is the opening note of hit number 10, the audio afterglow of the Big Bang. A computer sound analyzer reveals its strong tones as distinct columns on a color-coded graph. As hissy as the early cosmic sound is, it differs from pure white noise, which has no organized features at all on the analyzer. The sound of the audio afterglow, on the other hand, comes through with a vaguely musical quality. The pipes of this or any organ are made of wood and metal, but the pipes of the early universe were pits of dark matter, the mysterious substance whose existence is known only from its gravity.
What drives the sound waves is gravity. So, for example, if there's a region of slightly higher density of dark matter, there's a gravitational force pulling in. Gas that's surrounding this region feels that pull and it falls in, but it's gas, so it also, as it falls in, it compresses. That compression acts like a spring, and so it pushes the gas back out. But then it overshoots until it falls back in again. And this is how the motion of the gas falls in, bounces out, falls in, bounces out. So we have an oscillating pressure wave, a sound wave.
The cosmic background radiation, as important as it is just a still picture. Its imprint of sound has the effect of no more than one noisy, barely musical note. And even hearing that is a struggle. The pipe organ helps show us why.
The sounds of the universe are way too low for us to hear. In fact, what's the lowest note that this organ plays?
It is a pipe 32 feet long, and it can only be played with one's foot.
Yeah, that's pretty deep. 32 feet were nothing compared to the cosmic organ pipes. They were between 20,000 and 400,000 light years across.
Sorry, we don't have any pipes quite that long.
No.
The deep sound of the early universe is so low, we can hear it only after a massive shift upward. The background radiation of the universe dates from 380,000 years after its creation. But what happened before that? Is it possible to uncover the whole song of the universe from the very instant of the Big Bang? The cosmos is filled with a symphony of alien sounds, and we're counting down the top 10 of the universe's greatest hits. Number 10 on the playlist sings out with the earliest tones of the universe, from the audio afterglow of the Big Bang. But our download of the universe's birth song has some problems. With the cosmic organ playing all its pipes at once, what reaches our ears sounds like only one complex, noisy note. It's only one note because it comes from the pressure waves we read from the map of the cosmic background radiation, which is just a still picture of the sound in the early universe, taken 380,000 years after its birth. How then do we run the clock backwards and hear the rest of the song?
Modern cosmology is sufficiently advanced that it's possible to create a computer replication, a simulation of the young universe. It's possible to recreate within a computer what's going on and how the sound developed right from the very, very beginning through those first 400,000 years.
They are the same kind of supercomputer simulations that have given us pictures showing how the early universe evolved. The dark matter pipes of the early universe acted like those in the church organ. As bigger pipes were played, deeper notes were sounded. As the universe expanded, there was more space and more time. More space meant bigger pipes, so the notes in the song got lower and lower as the song played out. Put it all together, and the first 400,000 years of the universe can be condensed down to just 10 seconds. A haunting primal scream.
The gas that's falling in and out of these dark matter regions is ultimately going to become the first stars, the first galaxies, and ultimately it'll be corralled into the thousands of galaxies that we see around us today. So while it's been amusing, really, and playful to reproduce these sounds for us to listen to, in the big picture, they play an enormously important role in crafting the structure of the universe that's going to unfold and the universe that we find ourselves in today.
From the big band sound of the Big Bang, our countdown takes a step down in size to the modest 15 million light-year span of a galaxy cluster. Coming in at number 9 on our list of the universe's top 10 hits is The Deep Tone of Perseus. This is low sound to the extreme, emanating from the Perseus cluster, a grouping of roughly 1,000 galaxies, 250 million light-years from Earth.
The central galaxy in this cluster of galaxies has a huge supermassive black hole at its center.
The cluster's central galaxy is called Perseus A, and its supermassive black hole gives it what's called an active galactic nucleus, which shoots out energy in the form of gigantic jets, tearing into the surrounding space.
For reasons which we don't fully understand, it seems to be coming out, the energy is being produced episodically, about every 10 million years or so.
Those energy pulses are actually waves of pressure, and that's exactly what sound waves are. Pressure waves. The wave, as demonstrated by sports fans, has an up and down motion that's very familiar to us. But these UC Berkeley students will switch gears and show us how a sound wave is different.
Okay, everyone, lose the pom-poms. Since sound waves are pressure waves, we're going to build a pressure wave out of all these students. Okay, everybody, let's line up. You go over here and then shoulder to shoulder, just like this. Stretch out over there a little bit. No gaps. You're going to be students colliding with each other like molecules colliding in a sound wave. That's looking a lot better. Do you feel like a bunch of molecules? Okay, this is looking good. We have a bass drum at each end of the line. You'll see why in a minute. We'll get things going with this drummer over here. He's going to hit the drum and watch what happens. In this case, the pressure is a good, healthy shove, and it moves from student to student all the way down the line. At the end, the last student applies his pressure to the second drum by banging on it. This second drum is like our eardrum. When pressure from a sound wave in the air hits our eardrums, we hear the sound. This is just how sound travels through the air, except instead of having students shoving each other, there are air molecules shoving each other. A sound needs a medium to travel through. It can't travel through a vacuum. So in fact, to get from point A to point B, you need air molecules hitting each other. That's how it works.
So how do those pressure waves from number 9's deep tones of Perseus travel through what's essentially the vacuum of intergalactic space? Astrophysicist Richard Pogge of Ohio State University gives us a sense of the emptiness in deep space at his school's football stadium.
While it's true that sound waves can't travel through the vacuum of space, space is not a complete vacuum. I'm here in Ohio Stadium, home of the Buckeyes. It's very empty today. I'm the only one here, and can't think of a better place to illustrate the vacuum of space.
The empty stadium can be a stand-in for the vacuum of space if we compare it with what it looks like on game day. With more than 102,000 people in its seats, Ohio Stadium would be like the atmosphere on Earth, jam-packed with air molecules.
So how much do we have to clear out this stadium to equal the vacuum of space? Believe it or not, you have to clear out everybody, including me, and then even I'm too much.
No more than a single cell from Poggy's body could remain in Ohio Stadium to come close to the vacuum of deep space. With what seems like almost nothing in the expanse between galaxies of the Perseus cluster, the existence of sound waves seems all the more incredible.
How do you propagate a sound wave through empty space when it's mostly empty? Let's use the example of me running down the field. I have to run a long ways before I encounter somebody, but I still encounter somebody and I can pass energy along to them. The same is true of atoms in interstellar space. It has to travel a long ways, maybe 300 light years before it encounters another particle, but when it encounters it, it passes the energy and the wave moves along.
The colliding particles in the Perseus cluster also emit faint X-rays, whose traces, imaged by the Chandra Space Telescope, tell us the waves are there. But these waves are huge, and the notes they produce are lower than anything any human has ever experienced.
The pitch is about 57 octaves below our hearing, below the middle of a piano range, and that actually qualifies this for the Guinness Book of Records as the deepest pitch known to man.
The extreme deep note emanating from Perseus is so far below our hearing range that it can only be approximated. It's been said the galaxy cluster is playing an awesomely low B-flat, and scientists calculate it'll be playing constantly for 2.5 billion years. Number 9's Deep Tone of Perseus drones on as the countdown advances. A secret number 1 waits at the end of the line, but first, a strange high-pitched squeal hints at what comes in at number 8. Sounds from space and their link to signals from extraterrestrials. Starting with the Big Bang, we've been tracking the top 10 of the universe's greatest hits. The best of the alien sounds from space. Jumping to number 8 on the countdown, we find a sudden wide variety of different sounds. Clicks, whines, and screeches, all coming from strange stars singing out from everywhere we look in the galaxy. They're cosmic squeals with a rhythm section in the beat of the pulsars. Every pulsar has a different sound, but they are all related because they're repeating blips, beating out regular rhythms. The different sounds come from beats sounding out at different speeds. The first pulsars to be detected emitted radio waves so regular that astronomers first thought they were signals from aliens. But the truth about them was quickly discovered.
A pulsar is a rapidly rotating neutron star. That's a very dense star, and it's got 2 beams of radiation coming out the poles. As those beams rotate and intersect our line of sight, we see a series of pulses. We can think of pulsars being associated with sound because they were first discovered with radio telescopes. There was a series of beeps that radio telescopes detected. For a slowly rotating pulsar, you might have a series of beats like a metronome. Beep, 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 beep. Or you might hear a beep, 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 beep. Now, for a rapidly rotating pulsar, the beeps blur together, so you get like that. And for a very rapidly rotating pulsar, it's just a continuous sound that registers like a note in your ears.
Pulsars form from the collapse of very massive stars after they explode as supernovas. But how long does it actually take for a massive star to collapse? That's what Sherman D. of Tampa, Florida wanted to ask the Univers when he texted his question to us.
Sherman, the visible effects of a supernova can last for months or years, or even centuries if you're looking at the supernova remnant, the expanding gases. But although it may seem incredible, the collapse of the core of a massive star can take just a second or two, and that's what initiates the supernova explosion.
Our own sun isn't massive enough to go supernova, but it is a giant ball of hydrogen, 330,000 times more massive than the Earth and burning by nuclear fusion. So our home star can hardly keep quiet, as our next hit proves. This hot combo chimes in at number 7 on the countdown. Here it is, the Song of the Sun.
The sun makes sounds, but they're not really sunny sounds. They're not happy sounds. They're kind of low, ominous roars that gurgle along. The sun makes sounds because there are a bunch of gases going up and down through a process called convection. So they're sending pressure waves through the ball of gas that is the sun, and it kind of rings like a bell.
Unlike a bell, the sun rings with 10 million different tones at once. We detect them from the tiny bulges from the pressure waves on the sun's surface. Solar satellites measure the height of the bulges with exquisite accuracy. Apart from sound, they also produce science.
So using these sounds from the sun that we can observe, we can actually tell very detailed things about the interior structure of our star. For example, one of the amazing things that we can tell is when there's a sunspot group on the other side of the star, even before it comes around the limb and we're able to see it with our optical telescopes.
The sun may be the biggest source for sound in the solar system, but next in line is Jupiter. So coming in at number 6 in the top 10 is a medley of strange electronic jazz from Jupiter. Jazz from Jupiter comes to us courtesy of the 2 legendary Voyager spacecraft, now on their epic journey to the edge of the solar system.
The 2 Voyager spacecraft are headed for interstellar space. They're in the very outer edges of the bubble the sun creates around itself. Today, Voyager 1 is 118 times as far from the sun as the Earth is, almost 4 times as far from the sun as Neptune is.
Project scientist Ed Stone has been heading the Voyager mission since its 2 spacecraft made their grand tour of the outer planets beginning in 1979. On their approach to Jupiter, the first thing each one encountered was the giant planet's bow shock, producing a wind-like sound from the electronic data.
There's a wind blowing outward from the sun at about 1,000,000 miles per hour. It is supersonic. As that wind approaches contact with a magnetic field around, say, Jupiter, it has to go subsonic. There is a sonic shock which forms in front of the magnetic field of Jupiter. That's called the bow shock. It's very much like a sonic shock in front of a supersonic aircraft.
More intriguing than the bow shock is the Jovian chorus, sounding something like the chorus of birds chirping at dawn. Both it and the bow shock come from radio waves generated by fast-moving charged particles within the bubble of Jupiter's magnetic field. Now, the scramble toward the mysterious #1 in the top 10 swings to the moons of Jupiter and the rings of Saturn, where the noises from electric loops, glowing gases, and streams of wind vie for distinction as the spookiest sounds in the solar system. The top 10 countdown in the alien sounds of the universe has reached Jupiter, sending out its own brand of space music. But the next hit is no solo. Jupiter has a backup group. They're the Jovian moons circling the giant planet. And now they have their own album. It places at #5 in the top 10, and the tune is called Moons Over Jupiter. The lead singer is the moon Ganymede, recorded by the Galileo spacecraft, arriving at Jupiter in late 1995.
The sounds that Galileo sent back from Jupiter's moon Ganymede, by the way, the largest moon in the solar system, are very intriguing. They sound a little bit like an alien fax. In fact, when I played that sound clip in my office yesterday, people came around the corners to see what was going on, if I was receiving some alien transmission.
As with Voyager, Galileo's sounds came from ionized gas, or plasma. Atoms in a plasma are split apart into negative electrons and positive atomic nuclei. In other words, charged particles. Two slender antennas on the spacecraft's plasma wave instrument picked up the radio waves that the charged particles produced as they were set in motion by a magnetic field.
These sounds that we hear from Ganymede are the evidence that Ganymede actually has a magnetic field. And you cannot find that information without using the plasma wave instrument, as we did on Galileo.
A very sudden burst of alien sound came from another of Jupiter's moons. It happened when Galileo flew over Io's North Pole.
My favorite moon in the solar system is Jupiter's moon Io. It looks a lot like a pizza. This is the most volcanically active moon in the entire solar system, 10 or 100 times more volcanically active than the Earth. It literally spews tons of material into space every second, sulfur and oxygen atoms. These get ionized in Jupiter's magnetic field and actually connect back to Jupiter, to the north and south poles, making a donut.
The donut is called the Io flux tube, and the charged particles carry a monster electric current between Jupiter and its volcanic moon. As Galileo flew through it, the sound ended as abruptly as it started. With Jupiter and its moons finishing their acts, our countdown swings to Saturn, smaller than Jupiter, but right up there in the top 10. The ringed planet comes in at #4 on the list. Listen up for the surreal sounds of Saturn. They come to us from the Cassini spacecraft, which has been delivering mind-blowing pictures and data since its arrival at the ringed planet in 2004. As on Voyager and Galileo, Cassini's plasma wave instrument is our proxy for human ears in space.
The eerie and bizarre sounds we hear from Cassini's radio and plasma wave instrument make me think of Halloween. They're due to the aurora on Saturn, very similar to Earth's aurora. Your ears could never pick up these frequencies, but we move them into a range. And when we do, we were surprised to see how eerie and scary they actually were.
The surreal sounds of Saturn isn't the ringed planet's only song on the countdown. Turn it over and we find #3 on the playlist, Saturn's Flip Side. scientists call this hit a crossover. This crossover has nothing to do with mixing musical styles, but describes radio waves from Saturn's northern and southern hemispheres as they actually crisscross in frequency over a period of time.
We saw something really strange in our radio data, in our plasma wave data, a couple of crossing frequencies that apparently suggested that the northern and southern hemispheres were rotating at different rates. That's very unfamiliar to us on a solid Earth, where the Earth rotates at one rate. It actually turns out we don't think Saturn's rotating at different rates. We think that high-altitude zonal winds are tricking us and making us think that there's different rotation in the northern and southern hemisphere, but it's probably not the case.
Similar waves following the lines of Saturn's magnetic field revealed a surprise about the ringed planet.
One of the most bizarre things that Cassini found was apparently the Saturn day was about 6 minutes longer than it was back in the days of Voyager, mere decades earlier. The determination of the length of Saturn's day is actually not possible by watching the clouds rotate around the planet. We have to use these radio emissions, the sounds of space, to see what the deep interior is doing. And that's where we found this mystery.
It's virtually impossible to slow down a planet the size of Saturn that much in such a short time. So scientists now realize the radio emissions probably don't give an accurate picture. And by sophisticated mapping of Saturn's winds, they now have a better take on Saturn's day, which happens to be 10 hours, 34 minutes, and 13 seconds long. Now, we're closing in on the surface of Titan, Saturn's biggest moon, as it swings into the Alien Sounds countdown. Hit number 2 rings out as Totally Titan. And it opens with an otherworldly hiss from an actual microphone on the Huygens lander, separated from Cassini and parachuting through Titan's methane atmosphere nearly 1 billion miles away from Earth.
If you're parachuting, you're going to hear. That's exactly what we hear in these Huygens sounds.
The sound was transmitted as the lander headed toward Titan's surface in 2005.
The acoustic sensor on Huygens was essentially a microphone, but it only sampled every couple seconds. It would take a little sound, tiny sound bite, and then nothing, and then a tiny sound bite. It wasn't planned to turn that into sounds that the public could hear.
But unlike the other sounds from Saturn, these were not converted from radio waves. They began as true sound waves in Titan's methane atmosphere. And the Planetary Society stepped in to convert the staccato sampling of the microphone into something audible to human ears.
In the end, what you hear is mostly wind noise as the parachute's descending through the atmosphere, and then things get much quieter on the surface. It goes from to suddenly being. But what's really profound is we're hearing sounds taken by an actual acoustic sensor from 1 billion miles away. First time we've ever heard sounds from another planet or moon around another planet.
But the rushing wind wasn't the only sound coming from Huygens. As data streamed in from the lander on the way to Titan's surface, white-knuckled engineers in mission control held their breath, hoping the intrepid spacecraft would make its landing safely. The final chapter in the story is told in an incredible music video, guaranteed to keep you on the edge of your seat. We've been counting down the top 10 alien sounds of the universe, and we've almost reached number 1. But first, we're shifting into high gear, as number 2 runs with an astronomical riff from the Huygens space probe visiting Saturn's largest moon, Titan. It's the only alien sound that comes with its own music video. Look and listen. Cut 2 on number 2. It's Totally Titan.
Here we have what's called the Bells and Whistles movie from Cassini-Huygens, and it's showing the descent. And it's a great example of using sound to convey all sorts of different kinds of data.
Just as a Geiger counter announces radioactivity using audible clicks, the instruments on the Huygens lander were given their own sounds to register the measurements they were taking.
Those chimes you hear, each one of those means that an instrument was taking a picture or some other kind of data. Different instruments or a different chime. We also are hearing a kind of a hum in the background that's the signal strength to the Cassini spacecraft. We've got a ticking that occurs that has to do with the spinning and rotation of the spacecraft. Every time it rotates once, they have the tick.
Though it's just an assembly of pure scientific information, the video seems to preserve what must have been those last moments of high tension. When the scientists in Mission Control wondered, will the tiny spacecraft land safely, or will it crash?
So here we go, and almost down. And then we're landed.
Mission accomplished. With sound 1 billion miles away. Totally Titan has been a thrill at number 2 on the countdown. But now we spin the platter on the mysterious number 1. A song that comes from a place totally unlike anything else in the universe we've ever encountered. While some remind us of the strange signals from Jupiter and Saturn, there are also sounds in this song that are completely different from anything we've measured or detected anywhere else in the cosmos. Because number 1 on the countdown has sounds alien to the entire universe, except with a place where they originate. Number 1 in the universe's greatest hits resounds with echoes of a singular place. The echoes of Earth.
Here on Earth, we're used to thinking of the alien sounds as being everything that comes from beyond our planet. And that might be examples of plasma waves and pressure moving through astrophysical media or objects. But really, if you think about observing our Earth from afar, the aliens are us. And our sounds are unique because they come from living organisms, whether it be human language or bird songs.
An alien probe exploring Earth space would certainly pick up the Jupiter or Saturn-like sounds of charged particles propelled by Earth's magnetic field. But our planet, unlike the others, also emits radio waves, broadcast into the cosmos by human beings.
Good evening. This is Professor Reginald A. Fessenden, speaking to you from Brant Rock, Massachusetts.
In 1906, at Brant Rock, Massachusetts, Reginald Fessenden made the first radio broadcast of speech and music. Fessenden was the inventor of AM radio, transmitting his first signals on Christmas Eve. It was picked up by sailors hundreds of miles out at sea and has been traveling through space ever since.
Ever since the beginning of radio, we've really been broadcasting out into space. And we've been sending out these signals in the hopes that somebody will intercept them. Of course, space is a very large place, and therefore, it's hard to know who would have gotten them and when. But there they are, on their way out to who knows where.
Hello from the children of planet Earth.
Konnichiwa.
Earthly sounds are also traveling through space, not by radio, but aboard the 2 Voyager space probes, on a slow but steady course to the stars.
Bonjour tout le monde.
One of the examples of how important sound is to us here on Earth is that when we launched Voyager, we actually included a golden record of sounds from our Earth. And this was to represent not only human sound, but also sounds of the many creatures that live here on Earth with us. So it's really a sound fingerprint of life on our planet.
As we take our own place among the top 10 hits in our playlist, we realize they only scratch the surface of the cosmic voices calling out in the void. From creation to the present day, space has produced a broad catalog of sounds to accompany its brilliant sights. As strange as these many sounds seem, we've learned that they carry important messages, helping to solve mysteries of nature and our ultimate understanding of the universe.